Hello, my name is Ortega from the University of Grenoble in France, and I will present you a research I've made with David Furió. This work is the first study on the use of nonlinear perspectives in exploring 3D objects. First, what is nonlinear perspective? A perspective is a projection of a 3D object on a 2D plane. And most of our cameras today uses the linear perspective from the pinhole camera principle. It has several advantages. First, it's realistic, familiar because it's close to our visual system, but it's also widespread because every graphical card today is dedicated to its computation. However, with this perspective, you cannot access to all the faces of an object in the same single picture. For this, you need to manipulate and to turn around the object. And this is critical for some domains. For dentists, for instance, they need to see all the teeth in the same picture because they need to compare them and to measure them. This image you see here do not use the pinhole principle, and this is what we call nonlinear perspective. Another example is the Mercator projection, which flattened the Earth on a 2D map. As you can see, nonlinear perspectives have good advantages too, like reducing occlusion or giving access to specific tools. However, it's barely used. And the two main reasons are: first, it's hard to estimate the original shape from the projection, and next, the projection could lead to bad interpretations. For example, with Mercator, what gives you the intuition that Earth is a sphere here? Also, as the projection changes the proportions, what is the real size of a country? From these positive and negative points, we made the hypothesis that to be efficient, nonlinear perspectives should be associated or combined with linear ones. We therefore propose to integrate these two perspectives in a 3D visualization, allowing the user to control the transition between one perspective to the other. We implemented this idea on a tablet device prototype that uses pending movements to control the transitions. So let me explain you the principle. Here you can see a 3D house and a cone, which is a representation of a classical pinhole camera. The resulting image is this. We see the front face of the house. Now imagine that we display this image on a flexible tablet. The tablet is bent, making a convex shape. Well, what happens if I flatten one side of the tablet? Well, what we propose is to continuously transform the linear perspective into a nonlinear one in order to make it turn around the 3D object. The object therefore appears like unfolded, and one can see the side of the house as well as a part of the back faces. Here you see our prototype made with cardboard and tracked with an OTTrack system. We also tracked thumbs in order to give access to classical manipulations. To evaluate this idea, we conducted a study with 27 participants. We aimed at highlighting the benefits of using both linear and nonlinear perspectives against linear only. We created specific models, and the main task was to evaluate the length of a path around a big cube. We proposed 4 new techniques illustrated here, which are the combinations of bending shapes and perspectives. For example, with concave flat technique on the right, the initial shape is concave, and the nonlinear perspective is obtained by flattening the tablet. This study gave us first results. First, concave flat and convex flat techniques are promising in terms of performance, and next, the new techniques are preferred, perceived faster, less error-prone, and easier to use than the status quo.